Unit 1C, Lesson 2. The loan standard we're going to discuss explain why the x-coordinates of the points where the graphs of the equations y equals f of x and y equals g of x intersect are the solutions of the equation f of x equals g of x. And then we're going to find solutions approximately using various methods and discussing various functions. First, we're going to discuss a few functions. First one, absolute value function. The general form for the equation is y equals a times the absolute value of x minus h and then plus k. A few characteristics we can gain from this equation: the ordered pair of hk, that is going to be the vertex of the graph, and the value of a determines the steepness, basically our slope, as well as if the graph is going to open up or down. Okay, if a is negative, our graph will open down. If a is positive, it will open up. The absolute value graph is going to look like a V. For an example, suppose we want to graph the function y equals 2 times the absolute value of x minus 1 and then minus 3. First, we need to determine where the vertex of the graph is going to be. So we use the ordered pair 1, negative 3. Go over 1, down 3. This is going to be the vertex of our graph. We look at the value of a. It's positive. We know our graph is going to open up. So now we need to plot a few points. This value of 2, our a value, that is acting like our slope. So from this point, I can go up 2 over 1. Again, I can go up 2 over 1. Since this is an absolute value function, it forms a V. These points are going to be symmetric about this vertical line that goes through the vertex of this graph. All right, so I know that if this was a point, that mirrored image will have a point over here, and then if this was a point, we'd have the mirrored image across over there. Now if we connect these points, we have an outline for the absolute value function. The next function we're going to discuss is the exponential function. In its most basic form, we have y equals a times b raised to the x. If it's an exponential function, we can determine that by the variable being in the exponent. B is called our base. A is just a value that is being multiplied by, telling us whether our graph is going to be above or below the x-axis. A more common form we're going to see is y equals a times b raised to the x minus h and then plus k. H stands for the horizontal shift, and k is the vertical shift for the graph. Looking at the graph for an exponential function, first if we look at the left, we have f of x is equal to 2 raised to the x. When graphing exponential functions, it's easiest to create a table of values. If we look at this graph of y equals, or f of x equals 2 to the x, now we look to the right, we have the graph for f of x equals 2 to the x minus 4. So the only difference between these two graphs is going to be this minus 4 at the end, which means we have a vertical shift 4 units down. If we look over here, an easy point to compare, the graph went through the ordered pair 0, 1. So if this was a shift down 4, 0, negative 3 should be a point. If we look, 0, negative 3 is a point. The third and final function to discuss is a logarithmic function. Logarithms and exponentials are inverses of each other. Our base form is y equals log base b of the quantity x minus h plus k. A few key factors for this function: x equals h is a vertical asymptote, x greater than h is the domain, and the graph increases if b is greater than 1. The graph will decrease if b is between 0 and 1. Looking at an example, we have the graph of y equals log base 3 of the quantity x minus 1 plus 2. A few things we can look at: our h value is 1, so x equals 1 is going to be a vertical asymptote. Our domain is x greater than 1. We can see that by the graph. Only x values that are greater than 1 are going to be included in this function. Again, like we talked about with exponentials, when graphing logarithms, creating a table of values is going to be useful. Create a few points, plot those points, draw a smooth curve through them. If we look at our base, which was 3, 3 is greater than 1, so we know the graph is going to be increasing from left to right. To end this lesson, we are going to go through a simple example of solving a system of equations by graphing. We have two linear equations. First, we have y equals 2x minus 4. We plot the y-intercept, which is negative 4. Our slope is 2, so rise over run, up 2 over 1. Continue that pattern. Now we draw a line through all of these points. Now going to the second equation, y equals negative x plus 2, y-intercept of positive 2, a slope of negative 1, so down 1 over 1, continue that pattern. Draw a line through the points. When we're solving a system of equations by the graphing method, we're graphing our equations, we're looking for any points of intersection. Over here it looks like a point of intersection is 2, 0. How we can check and see if that is actually true, plug that ordered pair into each of these equations. So if I plug 2 in for x in my first equation, 2 times 2 is 4, 4 minus 4 gives me 0, the y value. Plug it into the second equation, negative 2 plus 2 gives me 0. So the ordered pair, or the point of intersection, is the ordered pair 2, 0. The solution to this system is not the ordered pair. The solution is just the x value of 2. So when we're talking about a solution to the system of equations, we're looking for any x value that gives the same y value to all of the equations. For instance, in this case, we had an x value of 2 that gave us the same y value in both equations, the y value of 0. In this lesson, we reviewed absolute value functions, talked about exponential and logarithmic functions. You need to make sure you have all the general form for each of those equations as well as the key characteristics. Make sure you have a basic understanding of those. We'll go through that more in depth in class. Also understand the concept of using the graphing method to solve a system of equations. We're looking for any points of intersection. What we're going to discuss in class, go more in depth with those three functions, and then use technology to plot these equations. Since they're more difficult when dealing with exponential and logarithms, it's very useful to use technology. We'll go through that together in class.